Alright, this next one is called the nth term test, to be able to see if we have a converging series or a diverging series. And I'll be honest, this one is probably the one that is used the least often and is the least helpful in terms of determining convergence or divergence. But it is definitely shown on AP exams a lot, not for you to actually solve it, but for you to analyze the work that has been done already in a problem. So basically what they're saying is you can look at a partial sum. So instead of going all the way up to infinity, we can kind of stop somewhere along the way. And that's what they're kind of asking you to do. So say, for example, like if we were only wanted for like the sixth partial sum, we'd be going up until you get to the sixth term here with all of the different individual parts. So you plugged in 1, you plugged in 2, blah, 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 all the way up until 6. Basically, if you can create some sort of equation here using a partial sum, then you can take a look at the limit of that equation. If the limit of that equation, of that sequence, converges to some number, then that means the series will also converge to that number. If you get to that limit diverges, then that means that you have, excuse me, also a series that will end up diverging. So easiest thing to do is just to kind of look straight at some examples here and see what we can do with them. So for example, this first example, if we just kind of write out a few of the numbers that we know as we're plugging in values. So you start with 1/2, then it would be 1/4, then it would be 1/8, and you could keep on going, forever and ever and ever. So really what we're looking at is the first partial sum. We're going to call it S1. If we did just the first term, you would have 1/2. If we did the second term, so 1/2 plus 1/4, we would get 3/4. If we did the third term, 1/2 plus 1/4 plus 1/8, now we'd have a term of 7/8. The question is, can we find a pattern that's happening here? Well, yeah, definitely. It ends up being that the numerator is always just one less of the denominator, and the denominator every time at the end has just been our biggest denominator, which is 2 to some power. So what we can say here is we can figure out an equation, and the equation is the denominator is always 2 to the n, the numerator is always 1 less than that. There's our partial sum. What we need to now do is take, hey, what's the limit as n approaches infinity for both of those? Limit as n approaches infinity. Well, guess what? You have the exact same power on top and bottom. When exponents are the same, that means you would divide the coefficients. Well, they're the exact same. Your value is just 1. So that means the partial sum limit is 1. That means this whole big thing is equal to a summation of 1. Okay? So a little bit tricky, but that's how it's going to look. More often than not, they'll look something more kind of like this problem. If we start plugging in some values, we would have 1/1 plus, actually, hang on, let me fix the problem here. I wanted this problem to be not a positive here, but a subtraction in between. So we have 1/1, and then we're going to subtract 1/2. That's the first term. Now when we plug in 2, I would have 1/2 minus 1/3 when I plug in n equals 2. And then when I plug in another value, plug in 3 next, I'd have 1/3 minus 1/4. Maybe you're starting to see a pattern evaluating here. So what's going to happen as I'm working through these? Well, I'm subtracting 1/2, but then I'm adding it right back. They're just going to cancel out. I'm subtracting 1/3, then I'm adding it right back. They're going to cancel out. It's going to keep doing that forever and ever until you get to whatever your final term is. Well, in general, it's infinity, which that doesn't help. But if we're going to use a partial sum, no matter what, we're going to get to, at the very end, just one term, the 1/n plus 1 at the end. So that means our partial sum is the 1 from the beginning, and subtract the 1/n plus 1 that's at the very end of this problem. There's your partial sum. That's what I can take my limit of. Limit as n approaches infinity of both of these. And when I do that, well, the 1 just stays as it is. The second part gives you infinity on the bottom, which is 0. So again, we get a partial sum of 1. So we've got 2 examples here where you get, using these partial sums, you can find that the series itself is equal to 1. Now, here's the last series, a series that is just 1. Well, since this is always going to be, just when we add up forever, 1 plus 1 plus 1 plus 1 plus whatever, that's just going to equal n no matter how many. The thing is, though, how many n's do we have? How many values do we have is what's going to lead up to it. So, but that is a fine example of a partial sum. Again, we need to take the limit as n approaches infinity for each side. Well, we plug in, that obviously equals infinity. That means this is a diverging series. It diverges because this value, this limit, does not exist. The limit was equal to infinity. And frankly, we could have figured it out from the very beginning, because from the very beginning, this value has to be approaching 0, whatever this sequence is. Okay, so like for example, this last problem, if you tried to plug in infinity just from your original values, this has to be approaching 0, and it is. In this case, we're not approaching 0. There's no way that this series could possibly converge. So that's, again, one of the major things to look at, is that basically if we have a series a to the n going from 1 to infinity, 0 to infinity, for whatever, and we have that the limit of a to the n does not equal 0, then it has to follow, then the series will diverge. Alright, so there's using the nth term. Again, doesn't happen too often, but mainly knowing that if you have a partial sum, all you have to do is take that limit and you will get what your summation value is.